Alright, let's get started. Lesson 2, Strength of Acids and Bases, Unit 9. Now, in the first lesson, we looked at some very important acid and base theories, specifically the Bronsted-Lowry acid and base theory. Remember that in that theory, a Bronsted-Lowry acid is one substance that donates a proton or a hydrogen ion to the base, and the base is going to be the acceptor of that. And in a Bronsted-Lowry acid and base reaction, where the acid donates a proton to the base accepts it, we form a conjugate acid-base pair. The acid will form a conjugate base, and the base is going to form a conjugate acid. And those acid-base conjugate pair relationships are important for you to know. In this particular lesson, we are going to focus on what makes an acid strong or weak and what makes a base strong or weak. So I have in your notes a very important table that I want to focus on for a moment, and you need to really pay attention to these details here. So on the left-hand side is essentially we got listed here acids. And these are going to be really Bronsted-Lowry acids. And on the right-hand side here, we have the Bronsted-Lowry bases. Oops, let me bases. Okay, so essentially, as we look here, according to this diagram, it appears that the acid strength gets bigger as we're moving up the table. And so that means the HI here is a very strong acid compared to CH4 down here, which is a super weak acid. So our weak acids are down here, strong acids are up the top. Okay. Now, if we look at the bases, it's just the opposite of the acids. The base strength is actually getting stronger as we're moving down the table, so which means that up here is going to be our weak bases, and down at the bottom of the table is going to be our strong bases. Now, a couple of things to point out here when we erase this to show you a few things here. When you look at this, what we're looking at is conjugate acid-base pair. So HI is the acid, well, its conjugate base is I minus. So what we see is that the strength of the acid, a strong acid, produces a very weak conjugate base. So the stronger the acid, the weaker the conjugate base. And I think I would actually write that down, is the stronger the acid, the weaker its conjugate base. Okay, just kind of write that down somewhere in your notes. All right, now we can see this vice versa then, is that as we get down to the bottom here where the bases are strong, so CH3 minus is very strong, it's going to form a weak conjugate acid. So CH4 is very weak acid. All right, so the idea is this: the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. All right, so you can also look at it in the flip side of this. Weak acids are going to make strong conjugate bases. Weak bases are going to make strong conjugate acids. All right, so it just depends on how you look at it in that terms. All right. Okay, so when we erase this. All right, so what I would make note of is, notice that we have the hydronium ion right here, which is an acid, and it's going to be considered a strong acid. Anything above the hydronium ion is considered a very strong acid, or just we'll say strong acids. All right, and down at the bottom here we have water. Okay, and of course water's conjugate base is going to be the hydroxide. Anything below this is going to be very weak acids. Okay, and so in the middle, between those, between water and the hydronium ion, are going to be our weak acids. All right. So if these are strong acids above the hydronium ion, then these must be very weak bases. Right? And between water and the hydronium ion, then these would just be considered weak bases. And then anything above water would be very strong, or we'll just say strong bases. Okay, so we have pretty much an inversely related situation. Strong acids create weak bases, weak acids create strong bases, and so forth. Okay, so that inverse relationship going on here. Just remember that acids that are above the table of the hydronium ion are always going to be considered very strong acids, and anything below water is going to be a super very weak acid. Okay, and then if you kind of get that thought mind in your mind, you should be able to get this down. The other thing I wanted to notice is that we have Ka values here. Now we haven't talked about the Ka value yet. Essentially, a Ka value is the equilibrium constant for an acid. So we've talked about equilibrium constants of Kc. Well, the Kc is Ka. It's just that we refer to it as a instead of a C because we're dealing with an acid. We can still look at it in terms of Kb's as well. Kb's would be considered equilibrium constants for bases. So Kb is also a Kc value. They mean the same thing. Exactly the same thing. All the equilibrium principles that apply to Kc also apply to Kb's and Ka's. It's just that we're dealing with equilibrium reactions involving bases or acids. All right. So one of the things I wanted to make note on this table is that the bigger the Ka value, in fact, let me erase this some more so we can write. All right. The bigger the Ka value, as we can see up here, the stronger the acid. So strong acids have very, very big Ka values. And weak acids down here have very, very, very small Ka values. All right. So we can always look and think of the acid strength by understanding its Ka value. All right. So anything really greater than 1 is a strong acid, and anything that is super tiny, less than times 10 to the minus 14, is considered super weak. But anything less than 1 is considered a weak acid. So all weak acids have Ka values less than 1. And maybe we should actually write that down. Is that Ka values that are greater than 1 are strong acids, and Ka values that are less than 1 are weak acids. Okay, you can think of the same thing with bases. If you have a Kb value, so a Kb value that's greater than 1, then you have a strong base, and a Kb value less than 1, you have a weak base. Okay? All right. Now, the idea here is, what do we mean by what does this actually mean, strong and weak? When we say weak and strong, what does this all mean in terms of what are we talking about here? Well, we're going to talk about that in just a moment. All right. So here's some points I want to make about relative acid strength. Okay. And we'll talk a little bit about what it means to be a strong acid and what it really means to be a weak acid. Okay, so essentially, the stronger the acid, the better proton donor it's going to be. So all strong acids, super strong acids, are going to be great proton donors. Weak, or we should say the stronger the acid, the weaker its conjugate base is, which we've just talked about earlier with that table. Stronger the acid, the weaker the conjugate base. In other words, strong acids make weak conjugate bases. A strong acid completely transfers its protons, or all the hydrogen ions, to water, leaving essentially no undissolved or undissociated molecules in solution. Now, we've talked about in the first lesson, we talked about that water can act as a base in the presence of a strong acid. And so if an acid is stronger than water itself, water will be a base and will accept a H plus from the acid. All right. Now, weak acids then are only going to partially dissociate or break down in aqueous solutions, and therefore exist in solution as a mixture of undissociated acid and its conjugate base. We'll diagram this in just a minute, so it'll make more sense. And then finally, we said that strong acids have very large Ka values, much greater than 1. All right? All right, so let's diagram this idea of a strong acid and a weak acid here. So let's say we have a strong acid, HCl. Okay, now HCl is going to be the proton donor. And so if we mix it in with water, water is going to be our base. Okay, so essentially water is going to pick up an H plus. And remember, when water reacts with an H plus, it really forms the hydronium ion. Okay, so what we would see then is that if we added, and when we erase this, added HCl into water, we're going to really see the hydronium ion plus the chlorine anions, and it's going to all be dissociated. So that's all that's going to be in solution is the chlorine ions and the hydronium ions. Nothing else will be in there. All right? However, if you have a weak acid such as HF, okay, now HF is going to, because there's water in there, HF will transfer. Let me rewrite this. So HF will transfer its proton to water, except HF is very weak, so it won't do a lot of transferring. So that means that in our weak acid solution, once we put it in there, there is going to be a lot of HF remaining. There will be some hydronium ion, there will be some fluorine ions, but the majority is going to still stay as HF. There's not going to be a lot of dissociation or transfer, we should say, transfer of the hydrogen to water because HF is weak. So we should have a lot of HF in our aqueous solution. All right? All right, so there are really 5 strong acids that I want you to know, to memorize, have down packed, okay? The first one you should know would be, let's do HI, which is hydrogen iodic acid, and then HBr, which is hydrobromic acid, and then HCl, which is hydrochloric acid, and then you have HNO3, which is nitric acid, and then finally we have H2SO4, which is sulfuric acid. So hydrogen iodic, hydrogen bromic, hydrogen chloric, or hydrochloric, I should say, nitric, and sulfuric acids are all strong acids. These are the 5 strong acids I want you to know for the test. Okay? Okay, let's look at bases really quick. The stronger the base, the better proton acceptor it's going to be. A strong base makes weak conjugate acids. So in other words, a strong base makes these weak conjugate acids, as we talked about earlier. Strong bases are going to completely dissociate in water, leaving essentially no undissociated molecules in solution. So it's very much like a strong acid. Strong acid completely dissociates in the water, or in other words, there's going to be a complete transfer of H pluses for the strong acid. Well, a strong base is going to completely accept those H pluses and dissociate completely in water. Whereas a weak base only partially dissociates in aqueous solutions, and therefore exists in the solution as a mixture of undissociated acid, and it's that should be base actually. Undissociated, we'll have to change that to base. And it's conjugate acid. Okay? So that should be a base. Alright, and then finally, strong bases have large Kb values, as we discussed before. Alright, so those are some important points to know. So let's look at a strong acid and what's going to happen here. Or a strong base, sorry. Strong base such as sodium hydroxide. When it's placed in water, it's going to dissociate completely into cations and hydroxide ions. So there won't be any sodium hydroxide remaining. It's just all going to be in the ion form of sodium ions and hydroxide ions. However, if you look at a weak base like ammonia, if you place that into our solution, weak bases are only going to partially accept hydrogen ions. So, for instance, water can be our acid, and it's going to donate some hydrogen ions to ammonia. And so you're going to form some NH4 pluses and OH minuses in solution. But most of it is going to stay as ammonia because it's a weak acid or weak base. It doesn't accept H pluses very well. So even though we'll have some conjugate acids and conjugate bases in there, most of it will again stay as ammonia, NH3. So what we're saying is that strong bases completely accept hydrogen ions and dissolve completely in water, dissociate, break down into cations and hydroxide ions. However, a weak base is not going to be the best proton acceptor, and so in the case of ammonia here, it's only going to sort of accept H pluses once in a while to form the conjugate acid and the conjugate base, but most of it is going to still stay as NH3, or the weak base, in solution, aqueous solutions. All right? I hope this makes sense to you. I know acid and bases are fairly complex in its complete understanding, so do your best with this lesson. If you need to go back and relook at this lecture video, come in and ask me questions. I'd be glad to help you out with it. We will kind of discuss more about relative strength of acids and bases in class a little bit more and relook at this. But for now, this is it for now for this lecture video.